Alright, I recorded this video earlier today, but when I didn't record the sound, so I'm doing something new. I'm narrating a video that has already been recorded, so I'm going to kind of give you the play-by-play once the problem starts. These are the homework problems that you were assigned tonight, and I wanted you to have access to the problems. So we'll start with number 47A. I'm not going to work all of them. So we have an ellipse, and they have asked us to write the equation of the line tangent to the curve. And so we're going to find that equation at the point 1, 2. So since we're writing the equation of the line, we're going to need our point slope formula, which is y minus y1 is equal to m times x minus x1. We have a point, so we're going to need slope. So obviously we need to find the derivative. So we're going to use implicit differentiation, and I get 2x over 2 plus 2y over 8 dy dx, because I'm taking the derivative of a y term, and the derivative of 1 is just 0. So in simplifying that, I'll get x plus y over 4 dy dx, and then when I solve for dy dx, I'm going to subtract x from both sides and multiply both sides by 4 over y, and I will get negative 4x over y. So that's my slope generator, that's my derivative. I'm going to substitute 1 and 2 for x and y, and when I do, I will get negative 4 over 2, which is negative 2. So that's my slope, which will go in place of m. And then I already have my x and y coordinates, so I have y minus 2 is equal to negative 2 times x minus 1. And that is the equation of the line tangent to the curve at 1, 2. Problem 54. We've been asked to write two lines, tangent line as well as normal line. And you just simply need to remember that a normal line is perpendicular to the tangent line. So I'll do this opposite reciprocal slope. So you can see I wrote perpendicular. And now I need to find the derivative so I can get the slope of the lines that I'm looking for. So the derivative of x squared is 2x, derivative of y squared is 2y dy dx, and the derivative of 25 is 0. Solving for dy dx, and subtract x from both sides and divide by y. Now I'm only going to do this with the point 4, 3, so the slope of the tangent line, when I substitute 4 for x and 3 for y, would be negative 4/3. Okay, come on, there you go, negative 4/3. And then the slope of the normal line would be the opposite reciprocal of that, which would be positive 3/4. Alright, now that I have my slopes, I already have my point 4, 3, so I'm going to go into my equation, put in my slope, put in my, and that should be y minus 4 is equal to 4/3 x minus 3. Actually, that should be y minus 3, but I'll catch that in a second. Okay, so I just realized that I had my x value wrong. It should be y minus 3 is equal to negative 4/3 x minus 4, and on the other side, y minus 3 is equal to 3/4 times x minus 4, and that gives you your tangent line and your normal line, and you can go back later to do the other point. Alright, here we're looking for horizontal and vertical tangents, which is what we did today in class. We know that to get the horizontal tangent, we're going to need to set the derivative equal to 0. So let's find the derivative. 50x plus 32y dy dx plus 200 minus 100 dy, or 160 dy dx, and the derivative of 400 is 0. Getting all my dy dx terms on one side and factoring, I will get 32y minus 160 equal to, moving the other terms to the other side, will give me negative 50x minus 200, and then I'm going to divide to get dy dx by itself. Now we know that horizontal tangent, we're going to set the numerator equal to 0. So Okay, let me write that up. Okay, so we're going to set our derivative, and in this case the numerator equal to 0, and I get negative 50x minus 200y equal to 0. This is much easier than the one we did in class, because you get the x value straight up, and you get x equal to negative 4. Now to get the corresponding y value, we would take negative 4, and this time we're going to have to go back into the original to get the corresponding y value, because we don't have a line or a curve that it's intersecting. So go back to the original. Now to get the vertical tangent, we're going to do exactly the same thing. Okay, so we're plugging into the original to get the y. Alright, Jernigan, hurry up. Okay, now to get the vertical tangent, we know that we're going to, from class, we're going to set the denominator equal to 0. And so when I set the denominator equal to 0, I get 32y minus 60 equal to 0. Solving for y, I will get y equal to negative 5. And same, just like I said for the horizontal tangent, the point, I have the y value, so I'm going to go back into the original function to get the corresponding x value that goes along with that. And I'll leave that work for you with the calculator. 64 is basically the same type of problem, vertical and horizontal tangents. So the first thing I'm going to need to do is to find the derivative, and then after I find the derivative, I'll set the numerator equal to 0 and the denominator equal to 0. So solving for dy dx, I'll get 2y plus 4, and moving the other terms to the other side, negative 8x, or 8 minus 8x. Getting dy dx by itself, by division, I get 8 minus 8x divided by 2y plus 4. So the horizontal tangent, I'm going to set the numerator equal to 0. Solve for x, pretty easy here, easier than what we did in class. So x is 1, and again I have to go back into the original function to get the corresponding y value. And I'm going to do the same thing to get the vertical tangents. I'm going to set the denominator, I think that says numerator, but we're supposed to set the denominator equal to 0. And so 2y plus 4 equals 0, y is equal to negative 2, and then I'm going to go back into the original function to get the corresponding x value. Problem 67 is a problem practicing logarithmic differentiation, which means that I have to use log properties to simplify this. And so I'm going to take the ln of both sides and use log properties, bringing the power down and using the product property, changing it to addition, bringing the power down and changing the division to subtraction. On the left hand side, the derivative of ln of y is y prime over y. The derivative of ln of x is 1 over x. Then I have, remember, the derivative of ln of u is u prime over u, so I get 3, which is u prime, over 3x minus 2. And the derivative of the last term, again, is u prime over u. So I get 1 over x minus 1 multiplied by the 2 that's already there. And we know that we have to get y prime by itself, so I'm going to clean that up a little bit. I can get 2 over x plus 3 over 6x minus 4, just distributing the 2, minus 2 over x minus 1, and all of that gets multiplied by the original function y, and it's kind of messy, but it is the answer nonetheless, and you don't really need to do anything else with that. And then finally, the last problem that I want to do is number 71, and it's a variable base to a variable power, which is how I know to use logarithmic differentiation. So I'm going to take the ln of both sides, and I'm going to bring down the power. Now on the left hand side, that's easy. The derivative of ln of y is y prime over y. But on the right hand side, I have the product rule. So I could rewrite that as 2x to the negative 1 multiplied by the ln of x. And it's still the product rule, but it might be a little easier to think about when I'm doing the product rule. So I have the first function, 2x to the negative 1, times the derivative of the second function, whenever x, plus the second function, ln of x, times the derivative of 2x to the negative 1, which is negative 2x to the negative 2, and that's just the power rule. I'm going to get y prime by itself, and I'm going to clean up the right-hand side a little bit. So that would be 2 over x times 1 over x, plus, and actually it would be minus 2 ln of x over x squared, because it had a negative power, and that gets multiplied by the original function, x over 2x. Cleaning up a little bit more, x times x in the denominator is x squared, and since they both have a denominator of x squared, I can do one more step of cleaning, and that would be to make one fraction, 2 minus ln of x over x squared, multiplied by x over 2 to the x. And so that is